Right, let us continue to question number 4.4. So now 4.4, it reads as follows. They say to us, calculate the value of x using other values given on the graph. Shame they didn't even have to tell us using. We know we can use that because this is Boyle's law. I said to you yesterday, when you're doing Boyle's law, use this equation. I repeat, when doing Boyle's law, use this equation. P1 V1 is equals to P2 V2. If you want to use this equation, PV is equals to nRT, you are absolutely 100% welcome. Again, here the problem is you are not given the value for temperature. You are not given the value of mass or number of moles. Okay, I understand. Yesterday, we were given the moles, we were given the temperature, but we used this, right? I said to you, if you wanted to use this temperature, depending on the value of R, the units of the value of R, there are many things that are involved. You're going to use the absolute temperature. You're going to use the absolute pressure and all of those things where you're going to have to convert. Like I said, for you at this point in time, converting, you'll convert when you get it in university, guys. You can convert, it's fine, we can do that. But the problem is that question, it only worth 3 marks. Even today, it is 3 marks. So using this, you're good to go. Okay? So these are the only two methods, Shame, apparently, that you can use. Using PV is equals to nRT and all of that. When I just use this one, I said it yesterday, and I'm not going to say it again. So using the numerical values that are provided, we have this pressure. You don't need absolute pressure. You can substitute the units as they are, okay? In this case, to determine X, right? In cubic centimeters. So what is the pressure? P1 and V1, this will be my P1 and this will be my V1. This will be my P2 and this will be my V2, right? So don't confuse them. So P1 in this case, it's 150 kilopascals. You can also substitute the units, okay? But I know you in high school, you don't. And then the V1, my beautiful people, is going to be 350, right? It's equals to P2 is how much? P2 is 400, right? It's 400. Yeah, it's 400. And then V2, it's X, which is what we are looking for. It's X, which is what we are looking for, remember? So you're going to say on your calculator, 150 multiplied by 350, we get 52,500. 52,500 rand. I wish I had that in my account, but I'm kidding. So 400 multiplied by X. And then we divide both sides by 100 because we are looking for X. Now, what is the numerical value of X? Then we can say X will be equals to 131,25, write the units, cubic centimeters. And then we are done. 3 marks. Imagine PV is equals to nRT. Hey, this is the quickest and the simplest way to do it. Right. And then 4.5. 4.5, it's... Oh, ASCII, sorry. Right. So now, 4.5, it says to us, like all, yeah, 4.5, like all real gases, we have ideal gases, we have the real gases. Like all real gases, this gas will liquefy under high pressure. Explain why this happens. I have a video where I was explaining all of these things. I'll send the link so that you can also go refer to it so that you can understand better. But now, okay, here they say, like all real gases, look, we have the real gases, we have the non-real gases. The non-real gases are also referred as not perfect gases. They are not perfect. Sorry, they are perfect gases. They are perfect gases. So the perfect, if something it is perfect, if something it is a gas, right, and it is perfect, what do you think about it? Gas it is perfectly scattered, like the molecules of gases, they look far apart from one another, and it's like there is no intermolecular force at all. That's how perfectly we can say about the gases, right? But real gas, even though the gases are far apart from one another, there is intermolecular force. There is attraction between the gases, right? That's a real gas. That's how we explain a real gas in terms of intermolecular force. But the non-real gas, it's a gas that doesn't have intermolecular force. Corey, it perfectly explains what gas look like. I get if you have a gas, you would swear like, there is no attraction between these two molecules because it's a gas and it makes sense for you to say that. That's why we call them the perfect gases. Why? Because they do not have interaction. They do not have interaction between the molecules. It will make sense to say this is perfectly a perfect gas. But a real gas in nature, there is no such as perfect gas. There is interaction between these two. There's attraction between these two or repulsion between these two. Right. Another thing is when you talk about the volume, right? When the gas it is in a closed container, um, and these gases are far apart from one another. It's like they do not have volume. It's like volume, it is negligible, right? Um, that's perfectly so. That's how we can say this is an ideal gas. This is a perfect gas. Ideal boyfriend meaning ideal man, a perfect man. You understand? Ideal means perfect. So when these gaseous molecules are far apart from one another, it's like they do not have volume because they move randomly and they move far apart from another. It's like they do not have it's like they do not occupy volume. It's like they are not in a 1 liter. It's like they are far. You can't even say they have volume. That's perfectly so. That's a perfect guess. But the real gas, they do have volume, Shane. Real gas, because of attraction, that attraction keep the molecules together so that they can occupy a certain volume. That's what we call the real gas. Okay. So now, with the basic that I have just told you right now, 5.5, 4.5, it says to us, like all real gases, the ones that have interaction, the ones that have volume, this gas will liquefy under high pressure. Let me tell you this. Because these particles are close to one another, I mean, sorry, that not that that close, because these particles they have interaction and they're within a volume. It's a real gas. So when you compress them, what is going to happen? You compress the gas. Sorry, when you compress the gas, the compressor will be here, right? And then volume will be decreased. And therefore, these gaseous molecules will cluster at the base. And therefore, these gaseous molecules will form a liquid, will liquefy. So this gas will liquefy under high pressure. How do we see it's a high pressure? It's because we compressed. They are experiencing high pressure. They're under high pressure because we compressed them. Okay. So explain why this happens, why liquefaction happens. You're going to explain what I have just told you basically. This is how you're going to explain it. It's a real gas. They have volume and they have intermolecular force. So this is how you're going to explain it. You say at high pressure, at high pressure, at high pressure, a real gas, né? A real gas molecules will what? Will occupy space. What does this occupy space mean? Volume. Space means volume, okay? Will occupy space and have a volume. And have a volume. Volume. This is the first point. Remember what I said to you? I said the real gas, they have volume, they have interaction, they have intermolecular force. The real gases, guys. But the perfect gas, they don't have those things because they are perfectly gases. It's what you see about gases. So another point is the attraction. The attraction, which is interaction or intermolecular force, the attraction and repulsive forces between the particles. Yes, between the particles, it's either we're gonna have three types of forces: repulsive, attraction, and attraction and repulsive. Ne? Because remember we are compressing, we're decreasing the pressure, so we're making those the gaseous molecules to come close to one another, but at the same time they want to repel each other, the gaseous particles. Ne? So the attraction and repulsive forces between the particles become significant. Significant. Thus, you conclude, therefore, thus, the what? The real gas liquefies under these conditions. Under these conditions. That's how we explain this. You need to, guys, you really need to understand these things. You really